All right, hi Chem 20s. This is a little bit of a lesson on bonding theory and Lewis formulas. If you were in the Block 3 class, you can skip forward through a little bit of this up to the point of the end of where I go over some bonding theory or where we got to yesterday talking about a full complete octet. And if you're in Block 4, you'll be able to watch from the beginning and follow through and take some notes down. All right. So, bonding theory and Lewis formulas. Bonding theory is essentially how electrons in a valence shell interact with other atoms and other valence shells with the electrons in them to create bonds which form molecules. So, we have two different types of bonds, one being a covalent bond or sharing of electrons, and the other being an ionic bond, which is a transfer of electrons. So I like to think of a covalent bond as something that is shared because if you have co-workers, you would share responsibilities, things like that. And for some reason it sticks that ionic sounds like iconic, and iconic people tend to steal the fame, and ionic bonds steal electrons or donate electrons. So we have a full transfer of electrons in ionic bonds. Now, at any point, if you want to pause the video to take some notes down, please do so you aren't just watching the video. If you do need to write notes down about covalent ionic bonds, etc., as we go through, please make sure you pause the video, write the necessary notes you need to, and then continue watching. Because I'm probably going to go a little bit fast here just to get through the video. All right. So, other parts of bonding theory. So electrons and energy levels close to the nucleus are held strongly by attractive forces. So if you remember, we have, we have protons and neutrons, which I'm drawing on the side here, that are in our nucleus. So I'm going to draw a lithium atom here. It's not going to be beautiful. So around our nucleus here, which is in the middle, okay, I have a ring of electrons, okay, and this is what we would call an energy level. Now, in my lithium atom, which I'll put down here, lithium, I have 2 electrons in my closest energy level, and in my energy level that is beyond that one, I have a 3rd electron. This is because my atomic number of lithium equals 3. Perfect. So when I look at this diagram, I have my 3 protons in the middle here, which are the 3 blue dots, and then I have my 3 electrons that exist in orbitals. Now, electrons in energy levels close to the nucleus, just simply due to attractive forces, if these are positive in the middle, these electrons are just naturally attracted to the protons in the middle. So we have orbitals that then surround our nucleus, and essentially what an orbital is it's the possibility of an electron to be found in a certain space. So there's a chance that there could be electrons held in a space here, or here, or here, or here on our energy level. All right, and valence electrons are electrons in the highest energy level of an atom. So in this case for lithium, this single electron in the highest energy level is its valence electron. Now valence electrons are the only electrons we're concerned with when we deal with bonds. Okay, so when forming bonds, like I just said, we're only concerned with the valence electrons. So a single electron in an orbital is called a bonding electron, and 2 electrons occupying the same orbital, are called lone pairs. So in our first energy level, we only have one possible orbital. So essentially, what that looks like is if I'm looking again at my lithium atom here, well, that's kind of a weird color green here. So if I'm looking at my lithium atom on the side on my drawing, in my first energy level, I can only have 2 electrons held in a single orbital. Whereas in my second energy level, I have the potential of 8 electrons, and those 8 electrons can exist that can be in a pair with this electron that's already there, like so. Okay, I can also have electrons here, here, or here. So where the green X's are represent different areas that we can have an orbital. So I can have, as you can see, 1, 2, 3, and 4 orbitals, each with the potential to have a pair. But in the case of lithium, I have 4 orbitals, but I only have a bonding electron in one of those orbitals. It's a single electron unbound to another electron in that atom. All right, so like it says here in the second energy, we can have 4 orbitals, each with 2 electrons, so making 8 electrons around total. So then we have something like that we like to call the octet rule. So octets essentially is 8 electrons that will occupy a valence shell. Most atoms like to have a complete octet. Now, of course, with every rule, there's a few exceptions, and with this rule, there seems to be several exceptions, but at least for this class, the octet rule will stand. So essentially what that means is that every time that we're dealing with an atom, there will be 8 electrons that surround it, or it wants to have 8 electrons. So if it doesn't, it looks to fill electron pairs with other elements. So it will use other elements to fill its bonding pairs or bonding electrons to make bonding pairs. All right, so orbitals may be unoccupied, or it may contain 1 or 2 electrons. So again, we have these orbitals here, and they can either be empty, like you'll see in this lithium atom, or it can have 1 electron, like we see here, or it can have 2 electrons. So electrons spread out to occupy an empty valence orbital before pairing up. So if I was to go around and make pairs around this lithium atom, the electrons would go 1 in each orbital, and then they would go back around and pair up when necessary. So because of repulsive forces, the electrons don't like to be paired together. So we have 1 electron in an orbital is unpaired, and it equals a bonding electron, and 2 electrons in an orbital is paired, and they're non-bonding electrons, or lone pairs is what we would call them. All right, so I'm going to go back here, and I'm going to do another example here where I look at drawing sort of a Lewis formula and explaining what I mean by talking about valence orbitals and valence electrons. So if I deal with something like carbon, carbon has 4 valence electrons. Now I know carbon has 4 valence electrons because it's in the 14th column, and my column number tells me the number of electrons I'll have in my valence shell. Now if I can't figure that out just by looking at the columns, I can draw the energy level diagram and to see that carbon has 4 electrons, in its valence shell. So when I do this, because electrons are repulsive and they like to fill up the orbitals individually first, if I was to go around, I would have 1 carbon there in the first orbital, 1 carbon here in the second, third, and fourth orbital. So I would have 1 electron in each orbital first. Now, just because carbon only has 4 electrons in its valence shell, this is actually what the Lewis structure of carbon would look like. So Lewis symbols are helpful tools to describe how atoms bond, and to draw these, we always start with an element symbol. So as you can see here, I started with the carbon, and then I added dots to represent valence electrons. So I know that I have 4 valence electrons here. So I'll write valence electrons. All right, and so I evenly distribute these around the carbon as if it were a square. So I start by placing valence electrons singly, or 1 at a time, into each of the 4 valence orbitals, and then I continue to fill, creating lone pairs. So this is what carbon would look like. Now, if I was to draw oxygen, however, oxygen, as if I look at my periodic table, I see oxygen has 6 valence electrons. So as I go to draw my Lewis formula, or my Lewis structure for oxygen, I start again by drawing 4, one on each edge of my element symbol, or one in each orbital, and then I continue by pairing up one there and one on the side here. So what I've done is I've paired these two. Now they will go sort of in order, so you should go around either clockwise or counterclockwise to pair up your valence orbitals, or pairing up your electrons. So oxygen here actually has 2 bonding electrons, which we see here, and 2 lone pairs. Okay, so this is what we would call lone pairs, or LPs, and this is what we would call bonding electrons. All right. So we've already gone over carbon and oxygen, and we can take a look also at phosphorus as well, or sulfur. So when I look at my periodic table again, if I'm to draw phosphorus, I believe phosphorus has 5 bonding electrons. So when I do this again, I start 1, 2, 3, 4. Sorry, when I said bonding electrons, I meant valence electrons, with a one pair bonded at the top. So when I go around my circle, I have create one pair with 3 extra bonding electrons there. All right, so if you don't understand what's going on here, I have provided you with some additional notes that you can start to take a look and understand how those elements are represented with a Lewis structure. All right. Now, as I continue, there's a little bit more we need to know about Lewis structures. I can actually represent a compound as a Lewis structure. So I have the ability of representing a compound as a Lewis structure. So there's about 5 steps we need to use in order to predict Lewis structure, and we always use the central atom, which is an atom that has the most amount of bonding electrons. So it has the highest bonding capacity, and in other words, for example, I'll go back to carbon here. Carbon has a bonding capacity of 4 because our bonding capacity is dependent on the number of bonding electrons present. So I have 1, 2, 3, 4 bonding electrons present, which means it has a bonding capacity of 4. If they were to be paired up, as in oxygen, which I'm just going to complete it here, okay, this is what an oxygen Lewis diagram would look like. My bonding capacity of oxygen is only 2 because I only have 2 bonding electrons available. So this is the only place that I can have another atom join in there. All right. Now, because I can only record about 15-minute videos at a time, I'm running out of my time for this video, so the second video will be determining Lewis formulas using this 5-step method to look at Lewis formulas for a compound. So this video is wrapping up, and if you go back to the website, you'll see the other video to determine Lewis formulas, and make sure you also follow along with the little note package that I've provided you with.